So the fixed speed and etc. These things in the next session we can understand, right? So as of now, what we have discussed is motor classifications, definition, operation, and classification. So AC, DC, special motors, and universal motors. That is one simplest what we call major thing. And after that, mechanical commutation and electronic computation. In the external computation, synchronous is this is the one classification. Right after that, clearly what I am saying is here motor classification only, but instead of saying motor classification here we can say that machines, right? Why here we are saying that EV machines? In the sense, these motors, actually these machines, okay, can be operate as motor as well as generator. Nothing but if you are looking for a traction motor application, okay, based on the motors chart, this chart, you can select a proper motor, right? Those can be operated as a motor as well as generator who wants to equip with a regenerative braking. Understand this point. For that application, commutator motor, nothing but DC only, right? So here permanent magnetic field is obvious one thing that can be used as a motor as well as generator without any external things, and wounded series and separately. All the DC motor in fact can be used as a motor as well as generator. This is a single set here. Just come to the commutator plus, in the sense these all are specially operated with the AC supply, you can understand. That is why I never mentioned here AC actually, but here I have clearly written the DC, right? Induction motor, synchronous motor, doubly silent. uh, just as I said, the silent is having number of varieties, so doubly silent is a different one. And here vernier is nothing but, in the first slide what I am shown is the rotating rotor is split into single linear thing. So vernier calipers, digital vernier calipers, if you see, this is the one best example, right? So induction also two different motors, right? Case motor is the best select what we call best option here compared to the wound rotor from the induction actually, right? So here rotor winding is short circuited simply, so you have all the controls from the stator, and that is very efficient also. Synchronous, in the PM synchronous motors, right, permanent magnets, brushless AC and brushless DC, right? This is one thing you can understand. So this is where you now you can see PMSM, permanent magnet synchronous motor. That is what brushless AC motor in other words, right? Both you can use for the traction. There is no issue. Doubly fed SR. What is that? SR. Doubly silent motor. What is that? SR? Switch reluctance. Okay, you can go for directly switch reluctance. Stator permanent magnet based, and there are a number of applications are there for the respected innovations. So there is a classification, you can see different areas. Still these are related to electronic commutations I have written. Somehow you can see these things in the what we call that door windshield, etc., stepper motor applications kind of thing, right? After that, anyone has any doubts here till? Yeah. Yes, I am continued actually so far 1.5 hours. Any doubts from anyone? Yeah, we have 16 members. Any doubts actually? No doubt from anyone? Okay, fine. I'm continuing to the uh, comparison session actually. So, how to select a motor? In this thing, you have to compare the motor in few parameters. That is what I am saying. This is very helpful for the innovation part of you. Okay. Then power density is the one thing you have to understand. So these all are the things what I am saying. Power density is nothing but per kg quantity of the all motors: DC motor, induction motor, switch reluctance motor, permanent magnet synchronous motor, and BLDC motor. Right? So per kg, comparing all these 5 motors, okay, comparing all these 5 motors and their weight, okay, power to weight, that is what simply power density of the motor, right? There is a one unit quantity. According to that unit quantity, this classification or comparison result I am showing here. So DC motor can give you the power density of 2 units only per kg, while comparing with other induction motor can give you 3, SRM motor can give you 3.5, PMSM can give you 4.5, BLDC can give you 5. So which motor can give you high power, right? That is what power density. Then this is the BLDC motor. This is the actual reason why few people are gone for only BLDC, even though that has very other problems also. Understood my point, right? This is SRM. What I am projected here, that is a natural SRM, not that permanent magnet switch or reluctance, nothing but the Tesla's one here. Because Tesla's one is just for the proprietary property, nothing but that is a closed source motor. They are not given to anyone. So that is their own property. What they have achieved here, I think out of the Tesla engineers, no one knows until unless they have the experimental results. So that is excluded here, right? So this is natural switch reluctance motor only. You see this natural SRM motor with the DCR induction motor, that is better inherently, first of all, right? And after that, efficiency, if you see, even that efficiency is also same as the power density. That is the another thing you can understand. This is where most of the people are fallen for the BLDC motor. Yes. Now let's come to the point of this controllability, speed and torque. In low RPM you need a high torque, and in higher torques you need somewhat above the base speed, what we call in the DC motors, below the base speed and above the base speed. In terms of AC, then rated speed and below rated speed, above rated speed, simply synchronous speed, asynchronous speed, these are the terms. So concluding all these things, so controllability is nothing but the speed torque characteristics. So in the speed torque characteristics, there is no match to the DC motor actually. That is clear thing here, right? So the torque and RPM functionality SRM is very low here, and uh, okay, join, right? So what someone okay, no questions, right? So yeah, for the controllability, there is no match to the DC motors. That is why if you see drivers of the induction motors, drivers are nothing but control circuitry of the induction motors and other motors. What we are doing in the variable frequency drive motors or vector control motors is nothing but how we can operate these AC motors as a DC. That is what this R&D is going on the power electronics engineer, simply, right? So variable frequency drives gives you the ability of an induction motor to control the speed and torque characteristics of AC motor as a DC. You can use the variable frequency for induction motor. You can use the variable frequency drive for the SRM, PMSM, and almost that BLDC is having that variable frequency drive inherently. That is different. That is why this is electronically committed, right? This is also electronically commutated. This is not electronically PMSM, and this is not electronically. These two are naturally commutated. That is beauty of the Nikola Tesla. Okay, right? But this DC motor is having that commutated. That is there. Now we can see the reliability, nothing but how much input you are giving to the speed controller and how much output you are getting. That is what I have taken into the controllability parameter. Don't comparing that point with the reliability point here. So while clearing that, here what is the thing, reliability, longevity, that is what the reliability here we have taken for the life cycle actually. So the life cycles of the DC motor is very less comparing to the other here every segment, right? So that is why most of the time DC motors fail in the longer runs, right? Yes, still few applications are there, but this is the comparison for traction, right? After that, cost parameters, if you see, PLDC motors are very costlier, induction motors obviously costlier. These costlier in the sense I'm taking that for EV application, okay. And if you are looking for these for what we call this last mile connectivity and two-wheeler, so these are costlier, okay. And light commercial vehicle, LCV, light motor vehicles, the four-wheelers, non-performance oriented. Up to that point, if you taken this comparison, that is where I am giving this data. So this is what the results for the performance oriented. This will be the best option, and BLDC motor is the worst options because BLDC motor is similar to the functionality of DC motor, but having the limitations. You can understand the cost point of view. This DC motor is high and BLDC motor is very less, cheaper comparing to the high performance driven, right? So for the high performance driven powertrain motor comparison, this cost is highlighted here. Understand my point here? So the induction motor, which is having the variable frequency and vector both, and the SVPWM and closed loop operation, everything is there. Then this induction motor is costlier in the wholesale phenomena. And now just see the noise levels, which is delivering more noise. Induction motor and BLDC motor, PMSM, both are delivering high noise. Understood my point? And this DC motor and SRM motors are very low noise. Now just understand that Tesla model Roadster, which is a fastest, I'm not telling that is a fastest. Okay, more people are confusing here. Thing need to be understand that Tesla model Roadster is the quickest actually. Understand my point? That is not the fastest. So what is the fastest here? That Korean vehicle Insignia or any German vehicle that Bugatti, Chiron, Varian, those are the things actually the fastest. Nothing but the top speed is very high there. What is the point here? We need to understand the quickest is nothing but quick acceleration. In just 1.9 seconds, you can reach the speed of 0 to 100. This is what the Tesla Model Roadster 2021 achieved. That is with the help of the switch reluctance motor and specially designed with the help of permanent magnets. That you can understand the noise levels inherently from the motor operating phenomena based on this classification. You can see that is very less, right? But now see the worst thing, okay, the maintenance part, okay, maintenance of every motor. Again I am keeping here as the cost high performance application only. I am keeping for the high performance application. If you count or and compare all these five motors, DC motor is the less is in the sense very cheaper for the maintenance, okay. Every motor is having high maintenance for the high performance. Obviously for a high performance, if you see that maintenance will comes into the picture for EVs also. So EVs are not at all maintenance free. First of all, you need to understand this point. And after that, motor comparison, okay. In the motor comparison, these are the three slides, three charts where you can understand this comparison for the motor will be happen in the uh, what we call three major points actually, okay. So as I said in the previous chart, that power density, nothing but power to weight ratio chart. So just now see here, which motor has the high power density? BLDC, right? So maximum power per kg which can deliver BLDC motor, right? This is one thing. You now just I am going to zoom this thing right now. Yeah, I hope it is visible to everyone. So the power to weight ratio comparison scale of 1 to 5, right? So just this is what I am seeing is this is just for the electric motors. Traction motors are different, right? So now which one scored highest thing here? DC brushless scored highest thing, right? This is the data uh, in the chart form. Okay, this is you have understand, right? Now this is very simple. Now you people whenever see this power to weight ratio, BLDC motor, and the next is induction motor and SRM motor. These are the three motors you can remember as it is, right, from the previous slide also. Now just we will see this point, cost of controller comparison actually. So why in the last slide the cost parameter I am shown in the high performance. Now you can understand without a controller motor operation is useless, nothing to see the motor operation without a good controller. So in today's scenario, what is the cost of motor is almost the cost of controller. Then now imagine what is the whole cost of the powertrain. Understand? Still in India, people who are looking to go for own startups are struggling to find a high performance controllers which is Indian made. Okay, I have few contacts on that part, that is different, but out of this is Indian paper my friends published actually in the 2015 I think from Northern University. Okay, so there what we have understand is the cost of the controller of the brushless DC motor is very high. Again, now comes to this point. Okay, here for the high power density you have alternatives, that is induction motors and SRM motors, right? Now come to one point here, cost of the controller. So if you remove the cost of the controller parameter, that BLDC motor is an highest option, then what is the thing here? SRM motor controller is also high. Comparingly, induction motor is very low. Then who is willing to spend more money? They can go for SRM motor, right? If they don't want the BLDC motor, right? Obviously, they will go for the BLDC motor first of all because they have huge funds and etc. Right? And after that, if anyone wants to go for the economical way, then what is the left thing? Induction motor. This is why from the 2009 Tesla is used this induction motor only, three phase, right? Now just we will see the cost of the motor, actual motor. Okay, so this is power to weight. Now the second thing we have seen the cost of the controller, and the final thing we are seeing the cost of the motor, single motor itself. So again, BLDC motor is having high cost of the comparison for the manufacturing or development, right? Next to that, DC motor as well as the SRM motor is having again same cost, right? Again here the induction motor showed superiority, right? So this is how when who wants to design a powertrain, after knowing that basics, this kind of analysis you need to do. And this is all the chart what I have showed is this is according to my powertrain requirement. Okay, that powertrain, the performance and etc are different actually, power levels and etc are different, right? So this kind of motor selection methodology from this slide and this slide you need to do for every powertrain when you are going for your own startup company, or you want to go for any startup to work as a powertrain engineer, at least applicational point of view also. That optimization, why the iPhone is very crazy in terms of their specialities. That software to hardware optimization is very good, and that is the what we call challenging product in terms of their climbings, right? So this is the thing you can understand here. This is the same thing I am helping you to understand the optimization point. After that, this is efficiency chart. You can understand DC motor brushed is having peak of 85 to 90. Okay, that is whenever it is new motor. AC motor again greater than 90. This is once again I will tell you the 10% loading. Then just understand, except the DC motor, everything is good. Okay, the slight difference 3 to 5% you can see here, right? At what cost? How much extra cost you are getting that extra what we call 3 to 5% efficiency? That is the one thing you can understand simply. This is everyone will see. That is what Indian today's two-wheeler manufacturers are projected. Peak efficiency is this much. Then what about the point everyone has to understand is that is comes under when 10% is loading and 30% is loading and 50% is loading. This is what powertrain loading indirectly what I am saying is. So DC motor is slightly differs at 10%. Why we are calling this 10% is light load conditions. Understood my point? Power to the vehicle which is having 10% is oftenly considered as with rider. Only single person is going on. Just you can also consider this data efficiency comparison with four-wheeler also. Understand? Most of the time we can understand that if a single rider is going, you can get higher mileage. If you are going to put extra loading, okay, full occupancy is there, then mileage is drops. This is not with EVs actually. This is with the engines also. But few people who are uh, negative spreaders for the EVs are still saying that when you are increasing the load, EVs are not giving you the range. You can understand that is because of this thing only. But the loading is here. You can understand if you want to increase the light load efficiency, light loading conditions of the vehicle, then that is also here only. That starts from the motor. So now just see, real DC motor is just having 70 to 80. This is very poor just comparing to the DC motors. Now said me that who wants to use this BLDC motor if you are gone for any application. If I am there in your interview panel, I am going to ask such questions only. Right? Luckily, no one is asking in this depth manner in India, but I suggest you people to understand. Okay, so the next thing, a quick comparison for the AC and DC. Right, this DC is including with the stepper motor and SRM motor and BLDC motor, everything. AC is included that PMSM and etc. Everything. So just quick comparison. Okay, low power demand to start. That is the beauty of AC, right? So there is no such thing here. So that is why I am reading easy installation, right? So low power, understood my point. Surge power is the one thing which is drains the battery very quickly. Understand my point? Instantly you have to pull a large amount of power. This is one thing you can understand according to the NEMA standard. You can understand the last slide. So that initial starting current, that is not going to uh, cross 3 times or 4 times. Those are standards actually, right? So I will give you that last slide actually. Then controlled acceleration, quick acceleration. These are the simplest things you can understand. Self-explanatory actually this table. Adjustable operational speed, adjustable torque limit, reduced power line distribution. This is when you go on for the high power applications, nothing but kilovolts, kiloamperes. There you can understand this kind of problems actually. Right after that, high starting torque, linear speed torque curve. This is kind of engine tuning thing you can understand. This is uh, DC motors are very what we call user friendly simply, right? So linear speed, the torque versus speed. If you understand the curve, there will be a linear acceleration. Nothing but the curve will cross from the zero path equally from the torque side and speed side, right? So that is the beauty of this DC motor. That is why this AC motor drivers like power electronics engineer, me and other my seniors and their seniors are trying that AC motors to operate as a DC motor, right? After that, speed control over wide range. This is one thing. Base speed, below the base speed and above the base speed. You can understand that, right? Simply, who has the knowledge of basics of electrical machines, right? Quick acceleration is the simple thing, right? That is where you can see even that permanent magnet synchronous motor, switch reluctance motor. Those are the things you can operate as a DC motor, right? Now, just comes to the conclusion. It is BLDC motors having highest efficiency, and induction motors and AC motors, which are falls under the traction motor category, having 90. Just a slight difference of 5% is there, but at what cost you can understand and apply in your real life, right? Next thing is motor cooling is the obvious choice, right? That is cooling is actually derived into two categories. One is forced or natural. One is what we call uh, optimum cooling, right? So optimum cooling, nowhere we can see in the existence as of the today geological conditions, because optimum cooling is you can also achieve when you have this forced cooling. So once you have the control set up for the forced cooling, you can also go for the optimized cooling. So there is no need for go for the optimized cooling. So naturally you can see natural cooling, right, as well as force. In the mechanical side implementations, right? So in the natural cooling, cooling pins will be there in the stator of the motor, right? And after the rotor, right, there will be a fans. That is forced cooling actually, okay? But most of the time, that is also treated as natural cooling, okay? That is depends on the application actually, right? In the forced cooling, liquid cooling is there most of the time because of the high currents and etc etc. So you can see that is in the high speed applications. So Tesla motors all are liquid cooling only, right? Even their power controlling circuitry, nothing but the traction controller is also liquid cooling, right? So that is one thing, right? These diesel locomotives which are there in the olden days, that is a kind of history, okay? I don't want to touch the history now because of the time restrictions, okay, today. So yes, Tesla Motors is having a 4-pole AC induction motor, okay, that is with a copper rotor. Actually, they are just given that copper bus bars in the rotor side also. So there is no specific winding actually. Copper slots they will give and they will put that bars actually, right? So that is actually inspired the logo, Tesla Motors today's logo, right? Model S, Model X are using this induction motors, right? And in the Model 3, permanent magnets are incorporated, okay? So what is that specific motor, okay? You can identify which is that motor, PMSM or any other. You can identify PMSM or PMSRM, right? Just so those are not used in the semi truck Tesla, okay, right? So the permanent magnets increased the efficiency, especially in the start-stop driving. So in city environment driving, you can often say this is in city environment driving, where there is usual traffic you can see, right?